All right, thank you very much. It's an honor to be here. So I will talk about the Polyhedral techniques in combinatorial optimization. So this has been around for quite a while. So you know, it's a study of convex hull of integer points, finding properties and using properties of it. And it's been written books about this. So 3 of my favorite books are here, and actually the first one is written here in Bonn by Kotte and Wiegen. But as it turns out, we have had a lot of progress, but very nice open problems remain for the most basic of problems. So we will talk about 2 of these questions today. So the first is about the matching problem, which may be like the most classic problem that we can efficiently solve. So I give you a graph with edge weights. Can you find a perfect matching of maximum weight? So here in red, you see a matching of weight 3 plus 2 plus 2, 7. And in short, we have very, very good algorithms for this question. So for biped graphs already 19th century by Jacobi, and for general graphs that significantly more complex, Edmonds gave a fast algorithm in 1965. So this is a problem we understand, but what if I change it just slightly? So instead of asking you to find a perfect matching of maximum weight, let me ask you, find a matching whose weight equals a given target. So how hard can that be? So that turns out to be a major challenge even today. So we have no efficient algorithm that finds a perfect matching of a given target weight. And what is more is that we have many evidence such algorithms must exist. We know that there is an algorithm, it just remains to find it. Okay, so I will come back to why we know that this algorithm must exist later on. The second problem that we're going to talk about is the traveling salesman problem. So this is, find the shortest tour of n cities. It's a nice, attractive statement. It's been studied since the 19th century. It's nice because there's like competitions, popular competitions for finding the shortest tour, even preschool assignments. And more seriously, like the paper that will kind of be very important of our and other people's work here is from 54 by David Danzig, Johnson, and Ferguson that solved the 49-city instance to optimality. So they used a linear program to solve this 49-city instance to optimality, and we struggle still today to understand the power of that algorithmic technique. And more generally, it's a major open question what efficient computation can achieve for this question. Okay, so that's the 2 problems we're going to study. So I will start with the matchings and then go to TSP. And what is kind of satisfying for me is that recent progress, although they are different problems, recent progress has used techniques that are similar between the 2 problems, so polyhedral techniques. All right, so let's start from the beginning. So we have a matching. What is this problem? So we are given an undirected graph. We want to find a matching of maximum cardinality. So here is a matching. And in fact, this is a perfect matching because I match every vertex is paired up with another vertex. Okay? So as I said, this is a special problem in CS. It's been studied in all kinds of models of computation. And what I will focus about here is on parallel computation. Okay? So, of course, Google and other companies love parallel algorithms these days, but that's maybe not the main motivation why we care about matchings in parallel computation here, at least. So one of my main motivations is that this relates to one of the unresolved mysteries in computer science, so let me comment on that. And the mystery is whether randomness significantly speeds up computation or not. Okay? So if you have access to random bits when you design algorithms, can you solve more problems efficiently than if you didn't have access to such random bits? Okay? And it's tempting to say yes here, I think, because there are many problems, after all, that we only know how to solve efficiently if we have access to randomness. So one example is polynomial identity testing. Say I'm given a polynomial that is the determinant of a bunch of variables. How do I verify whether this polynomial is identical to 0 or not? If I have access to randomness, you don't have to think too long. I just flip a coin and insert random values of these variables, calculate the determinant, check whether the result I got is 0 or not. That's a very reliable randomized test. As it turns out, if we don't have access to randomness, then the only algorithm we know is kind of trivial exponential time that just develops the whole determinant. Okay? Other examples where we only have randomized algorithms is like generate a prime in a given interval. Okay? We only have efficient randomized algorithms for that question. So if you're new to this, you may say, of course, randomness must help. Then at the same time, if you study complexity theory, you know that there's a lot of indications that randomness should not help. Okay? Why is that? So if you believe that crypto exists, like pseudo-random generators, then it cannot be that your algorithm for polynomial identity testing can distinguish this random sequence from a truly random sequence. Okay? So if you believe in crypto, then everything that is randomized should be able to be de-randomized. And one of my favorite results is maybe a little bit stronger, is by Pagliazzo and Vigdesson. They say that if satisfiability, which is this canonical empty complete problem, has no small circuits, so it has no sub-exponential-sized circuits, then any randomized polynomial time algorithm can be made deterministic. So in fact, we believe that randomization should not enlarge the size of the set of problems that you can solve in polynomial time. So that's kind of good news if you want to design new algorithms, because if this is true, our belief, then there should be a lot of algorithmic techniques that remain to be discovered. Okay, so that's one motivation why you want to understand, that's one motivation why people are interested in matching parallel computation. So let me now come back to that. So in parallel computation, as we should think about here, is that you have polynomially many processors, so I can distribute my problem a lot. But I need to be really, really efficient. I need to solve it in polylog time. So not like in logarithmic time in the size of the graph in the matching case, or polylog. If you don't, I don't go into detail here because it's not so important. What is important here is that a major open question is whether we can solve the perfect matching problem in parallel or not. And one reason that we care is because there are randomized algorithms. If you're allowed to flip coins, then we have known algorithms since the 70s. So the first algorithm was by Lovas in 79. He showed that, we can decide in randomized polynomial time, parallel time, whether a graph has a perfect matching or not. And the search version turns out to be more complex, so it took a decade until Karpov, Vigdesson, and then Mulmuli, Vazhani gave algorithms for finding a perfect matching if it exists. So if we believe that we can de-randomize all the efficient computation, at least we should be able to do this question, right? That we know a lot about. We have studied matchings for over 100 years, so we should be able to de-randomize this. Okay, so that's where we are at. So what do we know? We know a lot for restricted graph classes, but it's not even known how to do deterministically for bipartite graphs. So that's a little bit sad. But in 2015, and this is one of my favorite papers, Fenner and Guyatirov made major progress. So they showed that they basically almost solved the question. So what did they show? If I'm not using any coins, it's deterministic. The only issue, the reason that they didn't really solve the problem is that they use n to the power of polylog n processors compared to polynomially many processors. Otherwise, they completely de-randomized the randomized approach for bipartite graphs. So that's why it's called quasi, because what we call in computer science quasi-polynomial when it's n to the power of polylog n. So it's a lot of processors, but before this result, it was only known to do how to do it with exponentially many processors. All right, and what we did then was use polyhedral techniques to generalize this to general graphs. And I will come into a little bit about the polyhedral techniques. This was with Tarnowski, how the polyhedral techniques come in here, and then we will see that the same techniques are very useful for the trial and salesman problem. Okay, so now I want to describe a little bit the beautiful paper by Fenner and Guyatirov, because I like it a lot. Okay, so what is a basic approach for de-randomization? So you take an existing randomized algorithm and you show that you can run it without random bits. Okay, so let's do that. So let's take the randomized parallel algorithm 1. So they're all based on the TUT matrix. So this is some matrix associated to a graph whose determinant is not identical to 0 if and only if G has a perfect matching. So it's a determinant with a variable for each edge in the graph. This is the matrix and so on, but don't worry. What is important here is that the determinant is not identical to 0 if and only if the graph has a perfect matching. So now we know how to solve this. We just flip in random values. And now it turns out that you calculate the determinant in parallel. That was a result by Sank in 76. And this is the algorithm by Lovas from 79. Okay? So you take the TAT matrix, you take in random values, you can calculate the determinant in parallel. So this is, you can check whether the graph has a perfect matching or not. This turns out to be a little bit tricky to work with this algorithm, so we're going to look at the second algorithm, which is almost the same. Just bear with me, but it took a decade to come up with. So instead of replacing each variable for an edge by a random value, we now replace it by 2 to the power of the random value. Okay? So it's almost the same algorithm. Okay? Before we had a TAT matrix, we replaced each xc by a random value. Now we replace it by 2 to the power of the random value. So what's the gain of this? So this is Mulmula-Vazirani. The first gain is that they show that using this we can do the search version, we can find a perfect matching in parallel. The second gain for us, which is more important for us here because we want to de-randomize, is that there's this randomized step, and then there's this deterministic step. And this deterministic step is guaranteed to work if there's a very nice sufficient condition that holds. Okay? So there's a sufficient condition of the weight function that we select in the first step that guarantees that the second step will work. And the condition is that the weight function we selected in the first step should be what is called isolating. What is isolating? That's that the min weight perfect matching is unique. There's only one perfect matching that attains the minimum with respect to this weight function. If that holds, then the second step is guaranteed to work. It's not super hard to prove. Then the second ingredient they did was that they showed if we select this weight function at random, then with good probability, the weight function will be isolating. So we have a randomized parallel algorithm. So our only task here is to do a deterministic weight function in parallel so that the min weight perfect matching is unique. All right, so if we can do that, then we're all good. Okay, so now what did Fenneguer and Tiraf do? So in computer science, there's a lot of greedy, greedy algorithms and so on. But maybe one of the main insights was that you should not be greedy here, okay? So let me explain. So what do? All right, so remember, we want to show that there is a weight function that isolates the perfect matching, meaning that it's a unique min-weight perfect matching. So they say, let's look at a family, capital W, of nice weight functions. Okay, this is just weight functions that assign weight 2 to the power of I to weight each ei mod k, okay, for k going from 1 to n to the power 4 or something. So it's polynomially many weight functions of polynomial range. So it's a nice family of weight functions with nice properties, and our dream would be to say that for any graph with n vertices, there would be one of these weight functions that are isolating. Because if we could say that, then we would just run all the weight functions in parallel, and one of them would be guaranteed to work. That would be the dream, because then we would have de-randomized algorithm. We would just run all these polynomially many weight functions in parallel. One of them is guaranteed to work because one of them is isolating. Now, that's too greedy, so what they say, let me just select W1 first, and let M1 be the matchings that minimize this weight function. If there's a unique matching that minimizes this weight function, I'm done. Otherwise, let's just continue. Let's select W2, and let W2 be those matchings M1 that minimize W2, and so on. And I continue until I have found a bunch of weight functions so that if I minimize them lexicographically, the matching will be unique. Okay? So the question is, how many weight functions are necessary? We would like to say that there's only one weight function that would be necessary. And what they proved is that you need log n, at most log n weight functions. And that's why it's quasi-polynomial. So this log n shows up in the bound. So if you would prove that there's a constant number of such weight functions, you would have de-randomized, but they proved that you need to select log n. So for any n-vertex graph, there exists a way of selecting log n weight functions from this class, so that if I lexicographically minimize them, my matching, my minimizer is unique. So then you can just do weight functions by setting a lot of weight to the first weight function and so on. Okay, skipping the details. So from polyhedral perspective, what does this mean? I start with a convex hull of perfect matchings of my graph. I select W1, I minimize it, So now I'm in the convex hull of perfect matchings that minimize W1. That's a face of my polytope. If this face is a single vertex, I'm happy W1 isolated my matching. Now I select W2, I'm stuck on that face now, so W2 will stay in that face, and now I minimize W2 on that face. I might get stuck in a subface, select W3, I get to a vertex. Okay? So sooner or later, I will reach a vertex, but we wanted to select as few weight functions as possible. Okay? And the way they prove that there's at most log n weight functions is that they show that the graphs corresponding to these faces, their girth doubles in each step. What does that mean? So every time I select a weight function, the length of the shortest cycle doubles. But you know, the length of any cycle can be at most n, so I can double at most log n times. And for that, they use a very nice structure of the bitype matching polytope. Okay? So their progress measure to show that you can select few weight functions is that the girth doubles in every step. So let me explain why this is much easier. Oh, yeah. Right. Okay, so we have this bitype matching polytope. So it's known that a sufficient set of inequalities for describing the convex hull of matchings in bitype graphs is just to say, hey, the degree of each vertex should be 1, and you know every edge should have a non-negative value. So any face now is obtained by setting a subset of the inequalities to equality, which corresponds to dropping edges. So you have each face corresponds to a subface. Unfortunately, for general graphs, the convex hull is much, much more complex. So I said exponentially harder. Well, what is needed? So this is Edmond's matching polytope from 1965, and a low bound by Rothfuss, I think from 2014, shows that this is unavoidable. So if you want to write down the convex hull for perfect matches in general graphs, you need exponentially many inequalities. Okay, so what does this polytope say? So we have all the constraints from the bitype case, but we also add this constraint that for any odd set of vertices, at least one edge in your perfect matching has to go out of this set, right? If I have 3 vertices, there's no way I can pair them up. So one guy has to at least be paired up with a vertex outside. If I have 5 vertices, there's no way a perfect matching can pair them up. So at least one edge has to go out. And this turns out to be a sufficient set of inequalities to add to describe the convex hull of perfect matchings. This makes our progress measure harder, so we have to work hard to generalize this for general graphs. For example, even in this case, the girth progress measure fails. But let me give you 2 key ideas for general graphs. So first one is, if you're in a phase where some of these constraints are set to equality, what does it mean? So we have a set S, and we are saying that any perfect matching that minimizes this weight function has to have exactly one edge crossing this cut. Okay? So the only thing I have to decide is which edge crossing this cut will be part of a matching. So once I select which edge, the 2 solutions will decompose into independent instances. Because we know that there will only be one edge in the perfect matching crossing this cut. So once we decide which edge, they will decompose into independent subinstances. So this is kind of excellent news for divide and conquer strategy. We can divide the problem into 2 independent instances. And then okay, so that's the best friend for divide and conquer. And the second ingredient is that, okay, there were exponentially many inequalities, but as it turns out, any phase is described by very few inequalities. And moreover, they're what we call a laminar family of vertex subsets. So what is a laminar family? That is a family of subsets so that you have no non-trivial intersections. So either 2 sets are disjoint or one is a child of another. Okay? So it's a very nice structure to these phases, even though you have exponentially many constraints. In particular, any phase is described by at most 2n minus 1 equalities. Just, okay, this was a little bit technical. If you didn't follow, no worries. Just remember this picture. This picture will show up in TSP, so we will see that the techniques are similar, okay? So yeah, techniques transfer to asymmetric TSP. So let me end this section by just recalling that we use this to generalize to general graphs, but also that there was quite some results following this nice paper by FGT. First from May to the intersection, de-randomization, totally unimodular polytopes, and lastly, but not least, Anari, Vazirani, and Sarkovsky showed that how to do this for planar graphs, completely de-randomizing. And all these results used our excellent understanding of the associated polyhedra. So let me now raise two what I think is fascinating open problems in this line, that I am at least very interested in. So the first one is the one I stated in the beginning. Is there a perfect matching of weight equal to W? Okay. We don't know how to answer this question. Top K matching. Instead of maximizing the sum of weights of your perfect matching, find the perfect matching and maximize the sum of the K heaviest weights. We don't know how to solve this question. When I say we don't know how to solve it, I'm a little bit lying, because the algorithm that we saw, Malmely, Vazirani, solves this in randomized parallel time. So in fact, if we allow for randomization, we can use their very versatile algorithm to solve both these questions, even in parallel time. But if we don't have any random bits, we don't even have a polytime sequential algorithm. Okay? So this is really strange, right? So we have really, really fast randomized algorithm that runs in polylog time on parallel time, polynomial many processes. But if we don't have access to randomness, we don't even know how to solve these questions in polynomial time sequentially. Okay. So if you have progress on them, let me know. Okay. So now, please wake up if you lost you in the end, because now we go to TSP and we will see how some of these techniques transferred. Okay, so what is this question? Find the shortest tour of n given cities, like that. This one, another, I would say if matching is like the benchmark problem in P, probably like the trial salesman problem is the benchmark of NP-hard optimization problems. Okay, so actually that is one funny example that they managed to solve exactly. So what is the shortest way to visit all the 24,727 pubs in the UK? It turns out that answer is like 45 million meters approximately. This was solved by Cook et al. They have this, if you search, there's this Concord solver that is extremely good at solving practical instances of TSP. Okay. But, let's get back. So two basic versions. The symmetric, where walking from U to V is the same as walking from V to U. And then the asymmetric, where you have no such relationship. We look at the asymmetric here, the more general variant. Okay. So input, an edge-weighted directed graph. You think of the road network, but it's all, maybe uphill and downhill. So the distances might not be the same in both directions. And the goal would be to find a tour that visits every vertex at least once, and you want to minimize the total time traveled. Okay? So many of you probably have seen the version where you want to find a Hamiltonian cycle that visits every vertex exactly once. They are the same question, assuming the triangle inequality, which you have to assume because otherwise there's no hope to do anything with any guarantees. So if you assume the triangle inequality, these are the same questions. This will just turn out to be a little bit easier to work with for us. Because you could just shortcut your tour if you have the triangle inequality. So in graph theory, a tour would be, I want to find a subset of the edges that is connected and they are Eulerian. Eulerian meaning that the in degree should equal the out degree. That's my goal. Given a directed graph with edge weights, find a connected subset of edges so that the in degree should equal the out degree of every vertex. Okay. So now we can look at the famous relaxation that was first used in the 50s. We have a variable for each edge, or each road. How many times did you traverse this road? We want to minimize the total weight of our tour, subject to out degree should equal the in degree. This means that the sum of the edges going out of V should equal the sum of edges going into V. And then we also want to avoid situations like that you have subtours. So you say that at each subset of the vertices, there should be at least one edge coming in and one edge going out. So if I look at the undirected cut, there should be at least two edges, one coming in and one going out. So here I use the notation delta plus S to be a set of outgoing edges, delta minus S, set of incoming edges, and delta S to be the union of the two, where I don't care about orientation. Okay, so that's this famous relaxation. It's also called the Held-Corp relaxation because they give an efficient way of solving this relaxation. All right, so now, this is a relaxation. This, unfortunately, doesn't give you an integral solution back. It's an MPR problem. So now the question is, like, how good... So if this relaxation says that you can visit all the pubs with 1,000 meters, how many meters do you actually need to visit all the pubs? So how good estimation of the value does this relaxation give you? Okay, and that has puzzled researchers for decades. So how good is this bound in terms of the optimal Tor? And it's conjectured to be small. The only lower bound we know is 2 for asymmetric. And for symmetric TSP, the situation is similar, but the gap is smaller between the upper and the lower bound. All right. So let's see a little bit how can we get any upper bounds on this relaxation. There were previously 2 approaches. And they are kind of built upon that we have these 2 different constraints, the blue constraints and the red constraints. One is maintaining that the in degree equal the out degree, and the other one maintains connectivity. So the first approach was say, hey, if you don't require me to be connected, it's easy to find an Eulerian graph where in degree is equal to out degree. I mean, you could output the empty graph, but that's not interesting. You could also output cycle cover, it's called. Okay? And then the second approach is say, okay, if you don't require me that the in degree should be equal to out degree, it's easy to find a connected graph. That's called the minimum spanning tree problem. Okay? So let's see them in action. Okay, so let's look at the first one where it's easy to find Eulerian graph that is not necessarily connected. So the way that algorithm works is find a min cost cycle cover. It is called a cycle cover. It's a bunch of cycles of minimum cost. This has cost at most the cost of a Tor, right? Because a Tor is a special case of a cycle cover where we have one giant cycle after shortcutting. So this has cost at most opt. But unfortunately, it doesn't connect the graph. So what do? We select a representative in each of these components and repeat. We find a cycle cover. This has cost at most opt again. We repeat. We find a cycle cover. So here I had to repeat 3 times. So I got that final Tor of cost at most 3 times opt. Okay, so now how many times do I need to repeat in the worst case in order to find a Tor? I claim, you always find cycles. You always halve the number of components. So you need to repeat at most log base 2n times. Okay? But you need to be really unlucky, people, because you need to always find cycles of length 2, and your cycles must always be as expensive as doing the whole Tor, because these guys have also to be tight, right, for you to be log base 2n factor more expensive. So it seems like a very worst case analysis that this guy will get a log base 2n. Now it turns out that there are examples where it is a log base 2n approximation. And furthermore, it's wrong. Okay, sorry, I chose wrong slide. But okay, so there are examples where it is a log base 2n approximation. And furthermore, it's like far from trivial to improve. So there was like 20 years, we went from log base 2n to 0.99 log base 2n. So this is like only proving we are not super unlucky in each iteration. So let's just try to find a little bit bigger cycles than 2. And the world record using this method is 2/3 log base 2n approximation. All right, then so this was no asymptotic improvement on log base 2n, just improving the factor in front of it. So then to improve, the first asymptotic improvement was by Michel and some other people, and they used the connection to the spanning trees. Okay, so let me explain why this spanning tree approach is a little bit tricky. So maybe you know the Christofides algorithm for symmetric TSP, where you take a minimum spanning tree and you correct the parity. It turns out that there's a huge difference between the directed case, a symmetric case, and the symmetric. Because here, if you're unlucky, you may find a tree that is incredibly expensive to correct. So what's the algorithm? I select a minimum spanning tree, I forget about that the in degree should be equal to the out degree, and then I correct it. So for example, this guy has out degree 1, but in degree 0. He needs to be corrected. This guy has in degree 1, out degree 1, so I'm happy. This guy has out degree 0, in degree 1, so I have to correct it. I can correct the parity of these vertices in polynomial time by doing something called a circulation. So here, I would correct it by finding one red edge. Okay, so I'm very happy because the red edges were very expensive in this situation. In this example, I used one red edge to go back. So I found an optimal Tor in this example. Okay, so I was very lucky. Now, on the other hand, maybe I started with this tree that is also a minimum spanning tree. This is bad news. I need to correct this guy, this guy, this guy, this guy. And there's 4 units going from the left to the right. So no matter what I want to do, I need to use 4 red edges going back to correct that tree. That's incredibly expensive. You can imagine instead of 4, I can use 1,000 or 10 million. It's just, I couldn't draw 10 million. So in contrast to symmetric TSP, where all trees are easy to correct, in a symmetric case, it might be arbitrarily expensive. So this is a bad algorithm. What they observed is that there's a nice graph theory concept called fin trees that guarantees that the tree is not too expensive to correct. So Asapur, Gamas, Madeo, Vescaranza, they gave this first asymptotic improvement by showing that if we select a random tree, then we are not worse than log n over log n. Okay, so they use that we want to avoid this bad situation by basically selecting a random tree. And this connection to fin trees has led to a lot of progress, like constant factor for planar graphs. And the best upper bound based on this approach is actually polylog n. And this is very complex. This builds upon this resolution of the Carlson-Singer. So it's quite a very deep stuff. Okay, so this gets very complicated, and it's polylog n by Anario Vescaran. So what we will do is to give a new approach here. And see, it's a more related to the blue approach. Okay, so remember the blue approach completely forgot about connectivity. Okay, so instead of completely forgetting about the red constraints, we will say, hey, for a smart subset of these constraints, I still want what you find to find some connectivity constraints. Okay? So instead of completely saying, hey, forget about connectivity, do what you want, just find an Eulerian graph, I will have some connectivity constraints. And that's what we call local connectivity ATSP. So here the input is the same as ATSP, and I'm giving a partitioning of the vertices into partitions. And your goal is to find subtors, so in degrees equal to out degrees, so it's Eulerian. But you need to cross each one of these partitions. You don't need to connect the whole graph. You just need to cross the partitions that I gave you. Okay, so clearly a Tor needs to cross all these partitions, but I don't force you to do that. Just find me a subset of Eulerian edges so that you cross each one of these partitions that I gave you. And the punchline here was that we proved that if you can solve this problem, then you can solve the general question. Okay, so basically a Eulerian case with some more connectivity requirements is equivalent up to constants to the general problem. And we were able to use this to give a constant factor for some special kind of metrics, but unfortunately not for general metrics. Okay, until I got help by Laszlo Weg and Jakob Tarnowski. Okay, so what did we do? So one key insight is very, very related to what we saw for the matching problem. So basically, before we were able to solve this question for very special metrics, so what we asked ourselves is, how general are general metrics? Can we simplify general metrics? Okay. And this comes back to what we saw before, these laminar families. Just remember, a laminar family is a family of subsets of vertices so that you have no non-trivial intersections. So either two sets are subsets of each other or they're disjoint. Okay? Okay? And I claim, this is not me, this was well known, but consider an extreme point x star to this set of linear inequalities. Then an extreme point is defined by the degree cuts plus a laminar family of the greater or equivalent 2 cuts. Okay. Okay. Let me, between friends, we can throw away the degree constraints because they don't really matter for this. And then I just add a minus epsilon s here for infinitely small epsilon, right? That's the same problem. I just do it to simplify. I wanted to prove you this because it's not a hard proof. So now I've added an infinitely small epsilon. It's basically greater than 2. Now I want to prove that any extreme point here is defined by a Laminar family of tight constraints. Okay. Proof. Suppose towards contradiction that there are two tight constraints that have a non-trivial overlap. Okay, so I have that x star, the fractional value of the edges going out of A is equal to 2 minus epsilon A, and the fractional value going out of B goes out is 2 minus epsilon size of B. All right. Now, by inspecting the picture, you can convince yourself that the fractional value going out of A plus the fractional value going out of B is at least the one going out of A minus B plus the one going out of B minus A. That's just to inspect the picture. I don't expect you to understand it here. Okay, just inspect all the possible types of edges, and this inequality holds. But now you immediately reach a contradiction, because you have 2 minus epsilon A plus 2 minus epsilon B on the left is greater or equal than 2 minus epsilon A minus B plus 2 minus epsilon B minus A. You have subtracted epsilon A plus epsilon B here, and you subtracted only epsilon A minus B plus B minus A. So that's a proof that this extreme point here is defined by a Laminar family. Okay. So how general are general metrics? Well, we are given a general edge weights instance. We have no structure on the edge weights. But now we're going to solve our problem with respect to this linear program. So we solve the linear program, we get an extreme point, and we throw away all the edges that took 0 value. Okay? So we have general weights here, but after doing extreme point, throwing in some duality, we have a very nice instance. Okay? So let me describe what you get for free from polyhedral techniques like this uncrossing plus duality. So we had a general instance, but we threw away all the edges that got 0 value in the LP. Then we will have the following. We will have a Laminar family of sets, and the length of any remaining edge will just be the sum of weights of the sets it crosses. So the weight of this edge will be 1 plus 4, which is 5. The weight of this edge will be 7 plus 5 plus 2, which is 14. And if you have remaining edges in both directions, they will in fact have the same weight. Okay, so you have a graph where the edge weights are very, very special form. And then between friends, we can say that, hey, we're almost done, because this looks like a very special kind of metric, and that was what we hoped for. But then we had to do some more stuff. I just had a nice animation. You can not see it in the PDF, that we have to do more work, but it's too much to say here. Okay. So at the end of the day, what we got is this constant factor approximation with respect to standard LP, and it got pretty complicated. But luckily, Vera and Jens improved it. Is it the same year, even, or a year after? Hopefully a year after. So they improved it significantly. I think the most important thing that they improved it with was that it made it simpler. It's still complex, but it's simpler and a better guarantees. We have a 22, so the upper bound integral gap is now 22. The lower bound is 2. Okay, so let me just finish. Like the open questions here are immediate. So, for symmetric or asymmetric, for general metrics, the upper bound is 22. For asymmetric, the conjecture bound is 2. For symmetric, the upper bound is 3/2 minus epsilon. It's a breakthrough by Klein-over-Skaran from 21. That's slightly improved on Christofides, but the lower bound is 4/3. So the open questions here are kind of immediate. It's can you get tight bounds or even better bounds using other relaxations? Okay. I think summary. We use this polyhedral understanding to make progress on some matching, de-randomization for deterministic parallel algorithms. And kind of cool was that they also led to this progress on TSB that was seemingly unrelated question. There's a lot of problems that remain to be solved. I guess that's another conclusion. So thank you very much. Yeah.